What an honor it is to follow up on Dr. Martinez's presentation and hear about all the physics that I read about and cut my teeth on when I was getting into the field, and then see the transition to engineering and now really manufacturing, right? Thinking about how we're going to do this at scale in a cost-effective way. That's quite a bit what I want to talk about, and really from the perspective of a company that 12, 18 months ago was a quantum computing company just focused on building what looked more like these early lab prototypes, to now a company that's doing a lot more than just quantum computing, that's developed other related products that have very close synergies and is developing core infrastructure that we genuinely believe will be at the heart of every single quantum device. And really what's allowed IonQ to do this is really the first mover advantage that's given us the resources to invest in research, development, engineering, and manufacturing. And so, the scale of that investment, people think about how far away is quantum. Quantum is now, because of the amount of great investment, great talent we've been able to bring into the field. And for anyone who's been at these conferences in the prior years and, appreciates the scale of how much bigger this is, you're seeing it and you're living it right now. And so my goal for this presentation is to talk you through a little bit of the strategy of what we are doing, and how we've evolved to be not just a quantum computing company, but a platform and technology company that's powering the whole ecosystem. And I want to start by talking about the latest developments in our compute business, which is really the core of what is inspiring, I would say, the majority of the field to move forward. And I'll start with very one slide kind of history, almost in parallel to Dr. Martinez's talk. Of course, many of you probably know that IonQ is taking a different physics approach to build quantum computers. These are based on trapped ions, really nature's ideal qubits that are all identical, that out of the box nature gives them to us with 100% manufacturing yield, but then figuring out how to control and harness them and engineer them into larger and more scalable systems. And that journey is reflected both in technological milestones here, from our founder Chris Monroe's first demonstration of a quantum circuit in 1995 to the first systems that IonQ built powering on in 2017, putting eventually on the cloud. And now, really in the last year, again, like Dr. Martinez said, a focus on how do we manufacture this in a way that actually scales up to utility sizes. And so that's the roadmap that I'd like to spend a moment talking about, which is really the latest development for IonQ over the last year. And so this is a video that our team made maybe a couple of years ago to describe how our ion traps used to work. They were quite complex. We would levitate ions over the surface of a microchip. And while that microchip was fabricated in a scalable fashion, it was the fact that we had to deliver these complex optical systems via free space that made this quite hard to scale. And you can see the ions are also scaling in one dimension. And so this is really the workhorse for how we've built really high quality quantum computers for the past several decades, but is quite challenging to scale. And so in the last year, with the acquisition of Oxford Ionics, a really exciting technology that we've been keeping track of for a very long time, we have realized that we can integrate the controls that we use to run quantum logic operations for trapped ion systems into these same kinds of CMOS-fabricated microchips. And scale out, not just in one dimension, but now in 2 dimensions. So all of the controls you need to run the quantum computer are built into this chip. And really the threshold for knowing that this technology is ready is that in the last year, the performance of this capability in these devices is now better than anything else we can build using the old approach. It's actually a factor of 10 better. So the fidelity or our ability to faithfully run quantum logic operations is higher than in any other platform by about a factor of 10. And so this now gives us the confidence that we can start to turn our focus to semiconductor manufacturing, to take this unit cell that is working really better than any other platform and scale it up simply by scaling out the size, the die size of the processor that we fabricate. So this is a really, really exciting era for trapped ion quantum computing, where we're going to see this system scale up much faster and more aggressively because of this 2-dimensional leveraging semiconductor fab. The other side of this is we've also learned how we are going to run algorithms in a way that do not have errors as we grow the size of the machines. And I encourage for those of you with a more technical background to check out our technical blueprint. It's a 100+ page document. To summarize, it shouldn't be taken for granted that just because you have a quantum computer, you know how to run useful quantum circuits or run them in a way that doesn't have errors. There's a lot of hard work in building the microarchitecture, the compilers, the error correcting codes. And so, it's really taken a village and a very large effort from the entire community to develop these codes that we now are very, very confident and understand exactly, once we have these systems of larger scale, how we're going to run algorithms on them. And so that's just a 3-minute introduction to what we're doing in compute. Probably what most people are wondering, and the questions I get asked most often at IonQ is, what has IonQ done? What is their strategy in acquiring all of these companies and expanding into all these different domains? So I do want to spend a minute talking through why we are going in these directions, and starting with our quantum network and cybersecurity businesses. So as a company building quantum computers, we are often asked by our customers what the implications are going to be for their security. So we are really in the best position to be able to help them manage that transition that we've all heard and read the executive orders about are becoming more and more urgent as we advance quantum computing technologies. And so this is why, in addition to the migration to post-quantum cryptography, which we believe should happen everywhere, where it matters the most, we have really the most advanced and longest standing portfolio of technologies and how to actually harness quantum networking for secure encryption. And this is something that's deployed at scale in thousands of kilometers of networks worldwide. On the other side of it, quantum networking is also intimately tied to how we think about building quantum computers. We heard about the data center. So I spent 3 years at Amazon Web Services, and when I visited the data center, what struck me there was that it was really just a large and complex network. It wasn't a mainframe type system. It was a lot of small mass manufactured components connected in a network. So for these technologies to scale to hyperscale, they need to be modular and interconnectable. And this has really been core to IonQ's vision since the beginning. So for those of you with a technical background, you may have read this somewhat obscure physical review paper, from 2014 from IonQ's founder, Chris Monroe. Actually, the story is that a venture capitalist identified this and brought him this paper and said, this reads like a blueprint for building a company because you've got an architecture that's modular. And the idea is to take individual ion traps and connect them over optical links using the same types of fibers and same types of technologies that we use in the data center to connect processors and GPUs together. And more than 10 years later, we're still pushing and at the frontier of the same architecture. The graphics maybe look a little better than what Chris drew up in PowerPoint, but really it's a lot of the same components, but harnessing some new things that we've learned over the last 10 years of R&D about how to very efficiently interconnect quantum systems with photonics. In particular, the way that had previously been envisioned to interconnect two quantum systems was by having each of them emit the smallest amount of light possible, a single photon, and having them interfere or overlap at a detector. And the challenge here is that for any of us who have done optics know there's a ton of loss in these media. And so the rates at which you can run these networks is very slow. To put it another way, our networking technologies are all asynchronous. We have read receipts, we have handshakes, and that's how we establish high fidelity, high rate, reliable networking connections in the classical world. And so this is exactly what we have to do with quantum networking as well. We need technologies that you can put in your network that can faithfully accept and store and process information based on these single photons. And this technology that we've developed called a quantum memory is really what allows us to do this. And in certain of these networks, it allows us to move up to 50 times faster, which really pushes us over the threshold where we can start connecting these systems together and scaling them out in a data center. And so we have what I would argue is the world's most advanced quantum memory and networking platform that's really based on highly manufacturable integrated photonics, as well as state-of-the-art advanced packaging technologies. And without having time to go into this much later, hang on to these concepts because this is also where IonQ is heading next, realizing that we need to be able to manufacture some of these new technologies at scale. So, our quantum computing roadmap is published on the website, but I want to share, really for the first time, our quantum networking roadmap of how we're going to interconnect these quantum computing systems over the next several years. And in 2026, so this year, we're working on establishing that we can bring network connections between quantum computing systems with trapped ions above the thresholds for computing. It's about speeding up. In 27, we'll be scaling up to multiple lanes to provide the amount of networking bandwidth that you actually need to move real error-corrected quantum information across a network. And in 28, we'll be connecting these in with state-of-the-art processors. And what I also want to highlight is we're not building this technology just for our own trapped ion systems. It doesn't make sense to build a networking device that only works with one platform. We really want to enable all of the different platforms. So in R&D, we're expanding coverage to, I would say, what are the leading modalities, including superconducting circuits, in the coming years. And last but not least, one of the really the most exciting directions that we've come into is into our quantum sensing business. And I've explained the logic for why we're doing quantum networking. When we looked at quantum sensing and we looked at atomic clocks, atomic gravimeters, these are devices that can sense fields like gravity or keep track of time more precisely than anything else. We realized that what these devices look like were sort of the end state of what we wanted our quantum computers to look like. These were really rack-mountable units that could be manufactured in mass, but had all of the optics, the atomic physics integrated into packages. And so really a lot of the same technologies, the lasers and the atomic physics, had already been pushed forward by this industry. And what we realized is that we could expand the use case of applications we could provide using this core technology that we had built. And so the team at Vector Atomic, a company that IonQ acquired last year, has really pioneered the most precise atomic clocks that are commercially available, atomic gravimeters, and deployed these systems at sea, on land, and even in space. And so quantum technologies really are out there in the field. They're not just in labs. And it started with these quantum sensing technologies, and quantum computing and networking is really following in their footsteps. And so why are we doing all of these things? Is this just a portfolio of products? No, we think that actually by connecting these technologies together, we can offer unique solutions that are not possible if you only do one thing alone. And so I often get asked, why did you acquire a satellite company, last year? Well, the reason is not just to do, business in space. It's to take the satellite platform as a theater for deploying these technologies and accessing new markets. So, for example, all of us have, devices in our pockets that connect to GPS. So you're already relying on atomic clocks today. GPS is a network of atomic clocks that allows you to synchronize time with about 1 nanosecond, and that translates to about a meter of positioning. So that's how, for those of you who drove here or took an Uber, your car knew exactly kind of roughly where it was on the road. Well, the atomic clocks that we have at IonQ are about 1,000 times more precise than the atomic clocks that are deployed in GPS right now. So by putting this in that space theater and providing timing synchronization at picosecond instead of nanosecond, if you're able to provide that positioning to your devices, that's how you'd be able to tell not just where you are on the highway, but how far you are from the car next to you. And so that's kind of the next generation technology that is you can start to think about and deploy and bring to market when you have these different pieces in what we call the IonQ quantum platform that come together. And that's really what has driven the strategy between investing in these different new technologies and also infrastructure and theater for deploying these technologies. And this is something that it's not just a PowerPoint slide. These are some pictures of the hardware. We're actually en route to doing this. So we have the world's leading atomic clocks, time transfer systems. These have been validated and ranked as the leading platforms by NIST. We have a working satellite platform and an optical communications terminal, all manufactured in-house. These satellites have been are launching on roughly a quarterly cadence. So this isn't something that we have to wait many, many years for to start testing and deploying. This is something that we can do and leverage the momentum in the space industry. And we have, I want to highlight more than just the technology, also the teams that we've been able to assemble together. We have a space mission division that has a track record of actually taking these technologies on aggressive timelines and deploying them. And so that's really the exciting thing about being able to grow and expand the scope, leveraging a lot of the same physics, a lot of the same components, but accessing new use cases and new markets beyond just deploying quantum computers in a data center. And so the last piece I want to talk about is how this all comes together in terms of infrastructure and manufacturing and scaling, which is really the subject also of the final part of Dr. Martinez's talk, where we've realized that a lot of these technologies, particularly the advanced integrated photonics, the ability to not just manufacture wafers, but then assemble them and package them, is a bottleneck that needs to be addressed in order for the whole industry to scale. And so we realized it in our own computing business, in our networking business, but I've been a part of a number of quantum companies, and it was a challenge and a bottleneck everywhere, throughout my career. And so that's why earlier this year, IonQ announced its intent to acquire SkyWater, which is a domestic, US-based, trusted, accredited foundry with 3 locations in Minnesota, Texas, and Florida. And Dr. Martinez talked about 300 millimeter state-of-the-art fabrication. That is something that we will need and we need to aspire to. What we also need is to close the gap between transitioning technologies from the lab, whether it's university labs or R&D labs at companies, into the foundry. And that requires not high volume, the most specialized tools, but very, very low volume, highly specialized, customized fabrication by experts. And this is what SkyWater specializes in. And this is what we hope, as a combined company post-close, we can bring to the entire community, not just IonQ, to accelerate technologies. And to give you a sense of this, SkyWater already has some of the most advanced superconducting integrated circuits and multi-layered niobium routing, which could help to solve some of the types of problems that Dr. Martinez talked about. They have an advanced photonic integrated platform and advanced packaging. And at IonQ, we have some of the latest technologies that are emerging out of the lab, for example, required for quantum memory and quantum interconnect. So the marriage of these two in an open foundry model is something that I think is going to serve as the connective tissue for the entire ecosystem to scale up. We really think that this technology will be in all of the quantum devices, not just trapped ion quantum computers, but all the quantum devices we're going to see come to realization over the coming years. And so with that, it's really been a pleasure and an honor to follow in Dr. Martinez's footsteps here. Please reach out to me. I'm available today if any of these technologies are of interest. And just want to close on the fact that there's never been a more exciting time to be involved in the quantum ecosystem. It's all really coming to fruition now. And if you're not invested or haven't learned about these technologies, now is really the time, because I think next year this is going to be 10x the size of a conference than it is this year.